Hello, and welcome. Today we're going to be talking about simple harmonic motion, which is often abbreviated as SHM. Simple harmonic motion is just any type of periodic or repetitive event or cycle. This can be anything as simple as breathing. You breathe in, you breathe out. You breathe in, you breathe out. Or even your heartbeat is a continuous, repetitive, periodic event, hopefully. But today we're going to talk about two also simple examples. The first one is just an object attached to a spring. When we attach this ball to the spring, and then we pull the ball outward, we have to apply a force to stretch the spring. Then when we release the spring pulls the ball back towards its equilibrium position, but then it continues past the equilibrium position to there, which compresses the spring, and as a result causes the spring to shoot the object back the other direction, like such. And this oscillation will go back and forth forever as long as there's no friction. And so hopefully you guys remember from last year that the relationship that determines this type of motion is Hooke's law. And Hooke's law is defined as F equals kx. So in other words, the amount of force that's required to stretch the object this distance will follow this relationship. So if you want to stretch it this distance, x, it's going to require a certain amount of force based on the spring constant k. And the spring constant is determined based on how stiff or relaxed the spring is. So the stiffer or harder to stretch the spring is, the larger its spring constant is. If it's a real loose, flexible spring, then it's going to have a really small spring constant. So the next important term that we want to talk about is amplitude. So amplitude is this distance x right here of how far we stretched the object from its equilibrium position or its starting position. The equilibrium position is actually represented by this dotted line right here, and that's the position that the object will naturally come to rest at. So its position before you do anything to the system. So this amplitude is basically the distance stretched. And a lot of times we'll abbreviate it with a capital A. Next, we want to talk about period. So we've talked about period before, and we abbreviate period with a capital T. But a period is the amount of time required for one cycle to be completed. So, in this case, one cycle would be defined as if our object starts from right here, when we release it, it's going to go all the way forward and then come back. When it returns to its starting position, that's defined as one cycle. So in this case, the period is going to be the amount of time that it takes for it to go from here, all the way forward, and then all the way back to its starting position. The next important term that we want to talk about is frequency. And we abbreviate frequency with kind of an italics F. And so the frequency is the number of cycles completed in 1 second. So in other words, in a 1 second time period, how many times does this object bounce back and forth? And so as you can see, period and frequency are very, very closely related to each other. And it's very, very easy to confuse the two. And so I like to remember it in terms of their definitions. And that period is time divided by a number of cycles, while frequency is the opposite of that. It's the number of cycles divided by time. And so when we write it out like this, we can see that these two definitions are very similar to each other. And in fact, period and frequency are inverses of each other, meaning period equals 1 over frequency, while frequency equals 1 over period. Now it's very important that we keep these two definitions separate from each other, that we understand the difference between them. Because today we're going to talk about a new type of frequency, which is called angular frequency. And we abbreviate angular frequency with the lowercase omega, which looks like a cursive W. And hopefully right now you're thinking, well, that's the same variable we use for angular velocity. And it's true. It is the same variable we use for angular velocity. And the reason it's the same variable as for angular velocity is because it is the same thing. If we think about rotational motion, think about a ball spinning. We can calculate its angular velocity, which is how fast it spins in a circle. But its simple rotation in a circle is a periodic repetitive event. And so because of that, we can say that angular velocity or angular rotation is simple harmonic motion. So to see how these two are exactly related, let's look at angular velocity. We know angular velocity is defined as theta divided by time. So in other words, how many rotations does an object move through in a period of time? And so if we look at just one rotation is going to have an angle of 2 pi divided by time. But using the definitions that we just came up with for period, of period equals time divided by number of cycles, we can use that expression and solve it for time. And we end up with time equals period times the number of cycles. And then we can substitute this back into our definition for angular velocity. And we end up with omega equals 2 pi over period times the number of cycles. But remember, we're only talking about one cycle. Because we're only talking about one cycle, our number becomes 1, and we're left with 2 pi over t. And this gives us our definition for angular frequency in terms of simple harmonic motion. But because our period is very closely related to our frequency as well, we can also say that our angular frequency will equal 2 pi f. So either definition is acceptable. They're both the same thing. It just depends on what variables you have on hand. So then there's one more definition for angular frequency that I'm not going to derive for you, but we'll derive it later in class. Right now I'm just going to give it to you. And that is omega equals square root of k over m, where k is our spring constant and m is our mass. And so this describes the angular frequency of an object when it's attached to a spring in a system exactly like this one. And so using this relationship, we can calculate the period or the frequency based on the spring constant of the spring and the mass of the object attached to the spring. So this is a very important definition that we're going to use again here in a minute. So then the last thing that I want to talk about is pendulums. We're all familiar with the pendulum. The pendulum is just a simple object and a string, and on the bottom of the string we have some type of heavy mass, whether it be a weight, a ball, a pocket watch, or whatever it may be, and then it just swings back and forth. So it swings back and forth like that over and over again. This is an excellent example of simple harmonic motion because it's periodic and it's repetitive. So today we're going to talk about 3 different types of pendulum. Those 3 different types of pendulums are simple pendulum, which is pretty much what we've always thought of as a pendulum. It's a string with a heavy mass on the end. Second type is a physical pendulum. This is a pendulum that instead of a string has a rigid rod or object replacing the string. And there may or may not be a mass on the end of it, but it's something that's stiff. And then a torsion pendulum is actually more of a spinning motion instead of a swinging motion, but it's essentially if we have a large disc and we attached it to a string, and then we twisted it up in one direction and then let it go. And so it'd spin in one direction and twist itself back up, and then it'd spin back the other direction and twist itself back up in the other direction. This will happen over and over again. Today we're just going to talk about the first two types, a simple pendulum and a physical pendulum. And the reason we're going to talk about these two is because they're mathematically identical to each other. We'll talk about torsion pendulums a little bit later. So to start, let's go ahead and draw a picture of a pendulum. Whether this is a simple pendulum or a physical pendulum, it doesn't matter. But let's look at the force that causes a pendulum to swing. So let's say it's hanging straight down initially, and then you pick it up and you hold it to the side like this and you release it. The only force, well, the driving force rather, of the pendulum is gravity, Fg, which acts straight down. And so what causes it to actually swing back down towards the vertical is the component of gravity that's perpendicular to the string. This creates a torque on the pendulum, causing it to move back towards the center. And so as it swings towards the center, that torque gets smaller and smaller until it returns to a vertical position where now the torque is 0. So here in this vertical position, it has no more forces causing it to swing, but what it does have instead is kinetic energy. And so because it has kinetic energy at that spot, it continues to swing back up in the other direction, like such, where now gravity again is still working straight down, but now the component of gravity is in the opposite direction. So as it swings back up the other way, now gravity is slowing the pendulum down until it finally comes to a stop, and then it starts swinging back towards the center. And this goes on, it swings back and forth, and again, without friction, it'll swing back and forth forever. So a couple of things we want to identify. This is very, very dependent on this angle theta with the vertical, because as this angle with the vertical gets smaller and smaller, the gravitational component pulling it towards the center gets smaller and smaller. And as that angle gets bigger, the component gets bigger as well. We also have the length of the string, which I'll call L. For all intents and purposes, the length of the string will serve as the radius of our circle. Even though our object's not moving in a full circle, it is moving in a partial arc length. And because it's moving along an arc instead of a straight line, we want to treat it as rotational motion instead of linear motion. So, to start, we can start with Newton's second law of rotation, which is torque equals moment of inertia times angular acceleration. And so we can define both the torque and the angular acceleration just like we did in the past, where torque equals force times length, where again the length is the length of the string. And then our tangential acceleration equals radius times angular acceleration. But our radius in this case is again the length of the string, so this becomes L alpha. Or in other words, AT equals L alpha. I'm going to go ahead and solve this for alpha. So we get a tangential acceleration divided by length of the string. And so I can substitute both of these formulas back into our original formula, and we get FL equals IAT over L. And so we can see the two L's, and so those simplify nicely. But also I'm going to be a little more specific in my force, because we know it's the force of gravity, which is Fg or mg, but more importantly, it's the component of mg. And we can see that component is directly across or opposite of the angle, and so we're going to have to use sine. So I'm going to rewrite it as mg sine theta, and then because we have the two L's, we end up with L squared equals I tangential acceleration. So from here, we need to simplify our sine theta. Nobody likes trig functions. And because nobody likes trig functions, we're going to eliminate it from our equation using what we call the small angle approximation. So the small angle approximation says that as long as our angle is less than 10 degrees, sine theta is equal to theta. And so it's not exactly equal to it because, again, it is an approximation. So I'm actually going to write approximation signs. So it is an approximation, so it's not exact, but it is really, really, really close. And so I encourage you, grab a calculator and try it out and see how close sine theta is to theta. And so using that approximation, we're going to rewrite our formula as mg theta L squared equals I acceleration. So now if we look at our equation, we have way too many unknown variables. And so we can go ahead and simplify our equation a little bit using Newton's second law of linear motion, which is F equals ma. And we can use that in combination with Hooke's law of F equals kx. Because both of them equal F, we can say ma equals kx. And if we solve for acceleration, we get kx over m. I'm actually going to write this in kind of an unusual way of k over m times x. And so the reason I'm going to write it like that is because I want to emphasize this term right here. This term of k over m. And so if we scroll back up, we're going to notice this relationship that I gave you a minute ago, which also involves k over m. And so we can see here that omega squared equals k over m. So now let's use this relationship and substitute it back in down here. And so this will give us acceleration equals omega squared times x. So we can go ahead and substitute this back in there, giving us mg theta L squared equals I omega squared x. So we're almost done. The last thing that I want to get rid of from our equation is theta. We got rid of the trig function sine, but I want to get rid of the theta because angles just make things more difficult, and our angle is constantly changing in this process. And so the way we can get rid of theta is by using our definition of a radian. We know that 1 radian, or radians in general, are calculated as arc length s divided by radius. And so again, remember, our radius is being defined as L, or length of the string. And in this case, our arc length x is actually, we just defined it as x, where x is this distance right here that it's swinging back and forth, or the arc length. And so our definition for theta becomes x over L. So now let's go ahead and substitute that back in here for theta. So we get mg x L squared equals I omega squared x, where this is divided by L. So after that substitution, we can see our L's cancel out, and then our X's cancel out as well. And so it very much simplifies our equation, giving us mg L equals I omega squared. So our equation becomes much simpler after we do that. And then we can go ahead and solve for omega, which will give us mgl over I. Or just omega by itself will give us square root mgl over I. And so based on the previous definition, we go way back to the top, we can see that omega equals 2 pi over t. And so we can make that substitution and say, well, this must also equal 2 pi over t. And then we can go ahead and solve for period, and we get 2 pi square root pi over mgl. And so this gives us a definition for the period of a pendulum. And so hopefully right about now you're looking at that and thinking, that's not the definition that we learned last year for period of a pendulum. And you're right, because this is period of a pendulum for a physical pendulum. But remember we talked about mathematically, it's the same equation for a simple pendulum. The only difference is this equation accounts for the moment of inertia of the object that's swinging back and forth. And so if we have a physical pendulum, instead of a string, we would have some type of rod that would have a moment of inertia. But if we're using a simple pendulum, that string is considered to be so thin and light that it's negligible. So in other words, in a simple pendulum, the only thing that has a moment of inertia is the bob that's swinging back and forth. And so we can consider that to be a point mass, which has a moment of inertia of mr squared. So if we substitute that back into our equation, we get t equals 2 pi square root mr squared over mgl. But again, remember our radius is length, so we can say 2 pi square root ml squared over mgl. And we can see the squareds cancel and our masses cancel, giving us something that hopefully looks more familiar of 2 pi square root L over G. And so this, hopefully, is the formula that you learned last year for the period of a pendulum. But this is where that comes from. And this is a better equation because it accounts for all types of pendulum arrangements. And so if we have a rigid rod here instead of a string, then we can incorporate the moment of inertia for that rod, which is going to be 1/12 ml squared plus the moment of inertia of the bob, which is mr squared. And so we can get the period of that type of pendulum arrangement. So I know we've gone over a lot of material right now, so please, if you need to, watch this video again, take notes, and most importantly, if you have questions, ask them. So if you have questions, please be sure to ask and get your questions answered. Other than that, I hope you have a fantastic day.